I've been in networking for over a decade and decided to make some content to try to help others understand this industry. Understanding the binary system can be a little challenging, so we're going to start with learning some fundamentals about number systems in general. Then we'll apply those principles to the decimal system, which is one we're all very familiar with, and then we'll apply those to the binary system. So, the first principle of a number system is that we have a base. And the base tells us how many unique characters there are in that number system. Once we hit the max, the last unique character that we have, we increment the place to the left by one, and then we start back over again, and then we cycle through. And that's just how we count in any number system. The base also means that when we calculate the place value, and this is going to get a little math here, but when we calculate the place value, that base is raised to the exponent, and that tells us what the place value is for each of those characters. So when we start all the way to the right, that very first place value is the base raised to the power of 0. If we have 2 digits, then the next place over to the left is the base to the power of 1. If we have 3 digits, then the next place over to the left from there is the base to the power of 2, so on and so on. So every time we add another digit there, then the place value is that base raised to the exponent plus 1 there. So this kind of shows us how we get that place value, that we take the base raised to the exponent for whatever position it's in. So if it's the first one all the way to the right in that first position, it's the power of 0. Every time we add another position to the left, we increment that exponent by 1. The number value of the character that's there, we take that number value times the place value, and then that kind of tells us what the total value is for that place. I'm saying place a lot, value a lot. Once we look at the decimal system, this really will make more sense. So when we get the total number, this is the last thing here, is in order to figure out what the total value is when we have multiple digits, is we have to take each one of those digits, multiply it by the place value, and then we add all that up. All right, so here we go. So the decimal system, we have 10 unique digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is very familiar to us, pretty intuitive. When we count 0 through 9. When we get to 9, we run out of digits. We don't have any more unique characters. So we increment the place to the left by 1, which was a 0. Now it becomes a 1. And then we start back over at 0. So this is how we get 10. And then we continue counting up, then 11, 12, 13, 14, 15, all the way to 19. When we get to 19, we've hit the highest unique value, which is 9. So we have to increment the place to the left by 1, so that 1 becomes a 2, and then the 9 starts back over at 0. And then we start counting again, all the way up to 29. This pattern continues on and on. When we get to 90, we count 90, 91, 92. When we get to 99 at the bottom there, at 99, now both of the digits are at their max value. So we increment the place farthest over. And so we have a 1, then a 0, then a 0. Both those 9s roll back over to 0. This gives us the number 100. This cycle continues on and on. We get through 500. And then once we get to 999, now we've hit the last unique character for all 3 of those digits. Now the place to the left rolls over to a 1, and we reset all those to zeros, and that's how we get the number 1000. This continues on indefinitely. So in the decimal system, we have 10 unique values, but that also means that 10 is the base for the exponent for the different places. So when we calculate those place values, we use 10 as that base there. So if we were to actually figure out what these place values are, anything to the power of 0 is 1. So the furthest place to the right is 10 to the 0. That place value is equal to 1. The next position over is 10 to the power of 1. So that's just like saying 10. Anything to the power of 1 is itself. All right, so then we get to the next position over, which is 10 to the power of 2. This would be the same as doing 10 times 10, and then that would equal 100. So the place value for that position is 100. When we get to 10 to the power of 3, that would be the same as 10 times 10 times 10, and we calculate that out. That gives us a place value of 1,000. Most people have kind of heard this, that there's a ones place, a tens place, a hundreds place, a thousands place. The reason we call it that is because that is the place value when you multiply the base times the exponent for that position. All of this seems very intuitive to us because we work in this system day in and day out. We were born into this system. So it seems we don't really have to think about it. So now let's take the number 2,345, and we'll get to this other principle of, in order to find the total value, you have to multiply each position by the place value and then add those together. So 2,345. In order to get this value, we would take 2 times 1,000 because there's a 2 in the thousands place. Then we would take 3 times 100 because there's a 3 in the hundreds place. 4 times 10 because there's a 4 in the tens place. And then 5 times 1 because there's a 5 in the ones place. That's going to give us 2 times 1,000 is 2,000, 3 times 100 is 300, 4 times 10 is 40, 5 times 1 is 5. And so then we add all these together, and that's what gives us the number 2,345. This should be very familiar with everybody. We do this without even thinking about it. So now let's take this and apply it to the binary number system. So the first thing is the binary number system, it only has 2 unique values, a 0 and a 1. And that's it. So when we count in binary, we count same the way we start out in decimal, 0, then 1, and then we're out of unique characters. So now we have to increment the place to the left of the 1 and make that a 1, and then roll the 1 back over to a 0. So now we have 1, 0. This is not 10, this is 1, 0 because we're in a different number system now. So we can continue counting. After 1, 0, we get 1, 1. Well, now we have reached the max value that we have for each one of those places, so we have to roll those back to 0 and increment the place to the left. So that gives us 1, 0, 0. Again, this is not 100. If we were in decimal, this would be 100. This is 1, 0, 0 because we're in binary. So we would continue counting. We get 1, 0, 1, 1, 1, 0, 1, 1, 1. Now all 3 places are at their max value, so we increment to the left, add another position here, and then it becomes 1, 0, 0, 0. This pattern continues on indefinitely, just like in the decimal system. Because there are 2 unique values in the binary system, this also means that the base is 2, and that is what we use when we raise the exponent there for the place values. So the position all the way to the right is going to be 2 to the power of 0, which we multiply that, it's going to be a 1. Anything to the power of 0 is 1. The next position is 2 to the power of 1. Anything to the power of 1 is just that number, so we get a 2 for the second position. Then we have 2 to the power of 2. It was 4, so we have a 4 in the third position. And then 2 to the power of 3 is going to be 8. It's like saying 2 times 2 times 2. So these are our new place values. We have a 1s, a 2s, a 4s, and an 8s. So let's take a binary number and convert this to decimal. So we're going to take 1101 in binary and see what decimal value that comes up with. So to do that, we have to multiply each of the unique characters by their place values and then add it all together. So to start with, we have a 1 in the 8's place. So we'd have to do 1 times 8. We have a 1 in the 4's place, so it'd be 1 times 4. There's a 0 in the 2's place, so 0 times 2. and then a 1 in the ones place, so 1 times 1. 1 times 8 is going to be 8. 1 times 4 is 4. 0 times 2 is 0, and 1 times 1 is 1. So when we add all these up, we get a decimal value of 13. So this is how we would convert from binary to decimal. Let's go the other way and convert from decimal to binary. So we'll use a smaller number here just to show the concept. We don't want to have to deal with massive numbers and spend a lot of time with the conversion, because the concept is really what we're after. So we're going to use the decimal number 11, and we're going to convert that to a binary number. So the first step is we have to find the largest binary place value that is not greater than the decimal number. This sounds kind of weird. It makes a lot of sense in decimal, because if I'm like, okay, I want to count to 100, I don't need a thousands place to count to 100 because that's too big. So we're trying to find what's the biggest binary number that we need here, place value wise, in order to count to decimal 11. So to do that, we have to use the place values. So when we look at this, 8, the place value of 8 is less than 11. So we want to look and see, what if we add another place value? Do we get over our decimal number, or are we still under? If we add another place value to the left of 8, that would be 2 to the power of 4, which would be 16. 16 is larger than 11, so we don't need a 16 place value in binary if we're representing a decimal number 11. Just like you don't need a 1,000th place if you're counting to 100 in decimal. It's too big. You don't need that number. So now we know that 8 is the farthest left we need to go in binary in order to represent decimal 11. So we would place a 1 in the 8th place, since 11 is larger than 8. And then we need to take that, since we have accounted for 8 of that 11, we need to subtract 8 from 11, because we have that represented by the 8th place. So 11 minus 8 is going to give us 3. So now we compare that to the next place value that we have, which is 4. 4 is larger than 3, so we can't use that. We don't have any 4s that we can take away from 3, so we would put a 0 in that spot. So we continue on to the next placed value to the right, which is the 2's place. So we can take a 2 away from 3. So we'll put a 1 in the 2's place. We'll do 1 times 2 because we've taken 2 away by putting a 1 in that 2's place. So we have to subtract 2 from 3, and we're left with 1. 3 minus 2 is 1. So now we look to the next place to the right, and this is the 1's place. So our decimal value of 1 and our place value of 1, they're equal. So we can put a 1 in the 1's place here. And then when we multiply the binary number 1 by the place value of 1, that gives us 1. So we subtract 1 from the decimal value 1, and then that gives us 0. So at this point, we have finished the conversion because our decimal value is now 0. If there were more places to the right that we hadn't filled in, then all those would be left at 0. But this completes the conversion here. So the binary number of 1011 is equal to the decimal value of 11.